Before we get into talking about the polarity of molecules, let's review the polarity of just a bond. You need to memorize that if it is nonpolar covalent, when you have a carbon-hydrogen bond, or when it's bonded to itself. And then please remember, if you have a metal bonded to a nonmetal, that is called ionic. But ionic, it is polar. It's just extreme polarity where you have a transfer of electrons. With covalent, remember you're sharing electrons, and so it will be nonpolar or sharing equally if you have a carbon-hydrogen bond or if it's bonded to itself, like two carbon bonds or two hydrogens bonded together. Anything else would be polar. All right, let's look at a molecule. So a molecule can be polar too. And it is composed of the geometry and also the bonds that are found in that molecule. Here's our rules. There's two of them. Number one, if the molecule has at least one polar bond, then the molecule is polar. And let's look at methane, CH4. There are no polar bonds, and that's because there's only carbon and hydrogen in this molecule. And carbon and hydrogen, we know that bond is nonpolar. So that makes the whole molecule nonpolar. If you look at the electron distribution or the electron cloud, you're going to see that it's going to be very even around the whole molecule. So there's not going to be any polar or any polar areas. So any areas that are a little bit negative, a little bit positive. So this is a nonpolar molecule. Let's look at this next one. So all I've really done is taken that methane molecule and taken off one hydrogen and put a fluorine. So I still have these three are nonpolar. These three bonds are nonpolar, but this carbon-fluorine bond is polar. If I were to look at that bond, I'm going to see that it's going to be a little bit negative around the fluorine and more positive where the carbon is. And just this one polar bond will make the whole thing polar. I can look at the polarity of the molecule is going to pass through the center of the molecule and go up through that fluorine. So my molecule is going to be a little bit negative over here and a little bit positive here. If you look at the electron cloud, you're going to have more of a shift. So I'm going to have more of those electrons around here, just slightly. More electrons around that fluorine. The bond between the fluorine and the carbon, those electrons are going to be more around the fluorine than they would be around the carbon. And it makes the whole molecule polar. All right, rule number two is just an exception to the first rule. It's about symmetry. Here's the exception. If you have the same polar bond all around a central atom and there are no unbonded electron pairs, then the molecule is nonpolar. So we call this symmetrical. So now it's not a mirror symmetry, it's a radial symmetry. So that means you're going to have the same thing coming out of the center. Everything will be the same. Let's look at our first molecule right here. This is beryllium chloride. Notice that beryllium, there are two bonds coming out from it, a chlorine on each side, and it is the same bond coming out of that beryllium. Chlorine, looking at the periodic table, chlorine is close to fluorine, and so chlorine has a greater electronegativity. So I'm going to get a polar bond coming out this way, and I will get a polar bond coming out the opposite way. And because I have the same bond all the way around, this is a vector quantity and they will end up canceling each other out. So this will be a nonpolar molecule that has polar bonds in it. Let's look at this is carbon tetrachloride. So carbon with 4 chlorines. You can see I have the same polar bond all the way around. And so because of that, all their bonds will cancel out and it will be nonpolar. If there are unbonded electron pairs, it is polar. So anytime you see unbonded electron pairs, you know it's going to be polar. Let me give you an example. So this is methane, NH3, and let me draw the dot diagram here really quickly. When you look at each of the nitrogen-hydrogen bonds, we do find that they're polar. They're pointing towards the nitrogen. The nitrogen is more electronegative than the hydrogen. But when you come to these unbonded electron pairs, it's going to be very, very negative right there in that area of the molecule. And what ends up happening is we have our polarity go straight through up to those unbonded electron pairs. So we don't have the same thing all around the nitrogen. There's some differences. We have 3 of the same bond, but that unbonded electron pairs disrupts the symmetry. So this is going to be polar. So really, anytime you see unbonded electron pairs, you're going to say that the molecule is polar, except for some exceptions, which we'll talk about next. Let me do one more of these. If you look at water, so water is composed of a polar bond here and a polar bond here, and these add up to give the molecule polarity, so it's going right through that oxygen. So when you look at the electron distribution or the electron cloud, you're going to see that it's going to be a little bit more around this oxygen. And that's because of the 2 unbonded electron pairs. Now, there are some exceptions to this. So if you have these 2 shapes, so this one is square planar, and this is an expanded octet. So I just have 4 bonds in a plane. As long as they're the same bond, it will be nonpolar. So this shape, if everything is the same, it can be nonpolar. And the other expanded octet is this linear shape. So this is a variation of the trigonal bipyramidal, but I have 3 unbonded electron pairs. And as long as you have the same polar bond, in this case, the xenon-fluorine bond appears twice, they will cancel each other out and it will be nonpolar. So again, if you see dots, chances are it's polar, except for these 2 shapes. So let's just go through and let's just practice figuring out if a molecule is polar or nonpolar. And remember, this is what we're looking for. We're looking for if it has only nonpolar bonds, and we're also looking for symmetry. So if we have those 2 things, it's going to be nonpolar. Let's look at the first one, methane. We've seen this before. I can sketch this out. So carbon with 4 hydrogens around it. My carbon-hydrogen bond is always nonpolar. There's nothing here in this molecule to make it polar. Also, I do have symmetry, so for those 2 reasons, it's nonpolar. Let's look at ammonia, and I sketched that one out earlier also. And this one is polar because of those unbonded electron pairs. So I'm going to get overall dipole moment or polarity that goes right straight through the molecule. The next example is just one bond really between the carbon and the oxygen. It is a triple bond, but there's only one area where they are connected. And so this just goes back to the bond symmetry. So it's not carbon-hydrogen and it's not bonded to itself. So this is going to be polar. So in this bond, it's going to be a little bit negative over here and a little bit positive here. So this one is polar. Let's look at this next one. So we have N2. This is triple bond. And notice it's bonded to itself. And so this was nonpolar. And we have CO2. When I draw it out, it does look like this. And I know that the bond between the carbon and oxygen is a polar bond. But because it has symmetry, this would be nonpolar because it's the same bond all the way around. Right here, this is showing the electron density. You can see that if it's polar, it's a little bit more negative. That means it will have a higher electron density, or those electrons, that's where they will be. And if it's a lower electron density, that's where it will have that positive pole. We can quantify how polar something is. For example, here I have ammonia and water, and then this is nitrogen trifluoride. And we can quantify them. So this one is given a value of 1.47 debye is what it means. So it's just how polar it is. The larger the number, the more polar it will be. Water is a little bit more polar. And this molecule over here is less polar. Can you explain why? Why is it like this? Looking at that first one, I have the nitrogen-hydrogen bond is polar, and and I have a higher electron density over this unbonded electron pair. So it's a little bit more dense up there where that electron pair is. Around the water, look, I have two unbonded electron pairs. So that just makes it more polar, just a little bit much. And looking at the nitrogen trifluoride, the last one there, the reason for its lower polarity number is the fluorines are competing. So instead of the nitrogen being the most electronegative, in this case it's the fluorine. And so even though I do have these unbound electron pairs that spread up and concentrate the density there, it's a little bit more distributed because those fluorines are pulling on the electrons in the bond more. And so it will still be polar, but just not as polar because there's three fluorines that are competing, so to speak, with that unbonded electron pair. The three down here at the bottom, we have a zero dipole for all three of these, and that's because of the symmetry. They all have the same bond all around a central atom, and so their polarities will cancel out. And this first one doesn't even have polar bonds, so for sure that one's going to be nonpolar. These bonds are not still, they stretch and they bend. So when you look at a molecule, IR or infrared spectroscopy, you can get these little wiggle peaks right here. And from them you can determine what molecule you have if you have a sample. Let me show you one of those. So this is a sample IR spec. This is more of a second year college chemistry type thing, but I just wanted to show you how the bonds, they wiggle and they stretch. And if you have an unknown, you get a printout of the IR spectroscopy, you can actually go through and identify the parts of the molecule. For example, this is a COO stretch, and this is a OH stretch here. This little OH group tells you that that's part of the molecule, and so you can see it right here in this molecule. So we use that stretching to help us identify what molecule it is. You can take a look at the stretching of molecules by visiting this website. If you just type in models 360, it should come up, and it can show you any Lewis diagram, and it can show all the polarity. So if you have any questions about a molecule, if it's polar or not, this is a place where you can go to type the formula in and to play around with the molecule a little bit to figure out if it's polar or nonpolar. So let's classify each of these molecules as being polar or nonpolar. So I'm just going to sketch them out. Nitrogen has 5 valence electrons, so I'm going to connect my hydrogens right there. So we've actually seen this one. This one is polar, and the reason why it's polar is because it has unbonded electron pairs. Let's do the next one. So we have SF6. So sulfur has 6 valence electrons, and I do have 6 fluorines there, so I am going to connect each of those fluorines where the dots are, and you should have 6 dots around every fluorine. But I can see I have the same bond all the way around a central atom. This one's going to be nonpolar because it has symmetry. Remember, symmetry means you have the same bond all the way around. Let's do the PF5. So we have phosphorus. Looking on a periodic table, it is in the nitrogen family also. So it looks like that. So I'm just going to connect those 5 fluorines around there. So 2 coming up and down, and then 3 are beyond this plane. This is a trigonal bipyramidal shape, and I don't have any unbonded electron pairs, so this one is going to be nonpolar. And let's do our last one. So we have carbon with a chlorine and 3 hydrogens. So this is a tetrahedral. And this one's going to be polar. And that is because it does not have the same bond all the way around. It has this carbon chlorine bond, and that's what's going to make it polar. So the ones that are polar are this last one and the first one.